Hello and welcome back to Calculus 3. This is class 3. We're talking about dot products, plural. I have to put that S there. Dot products. So we talked about vectors in 2D. We talked about vectors in 3D. We said that vectors can be scaled up or down by multiplying by a constant. And we also said that we can add and subtract vectors. Can we multiply vectors? And the answer is yes. This is one way to multiply vectors. And then we're going to learn another way, 11.4, called the cross product. So we are going to start first with the dot product. So the dot product in 1D is your regular multiplication. You hopefully know that 3 times 5 is 15. That is the dot product in one dimension. How does the dot product look in 2D, 3D, and ND? Well, we have the formula for that. The product in the dot product is always a scalar number, so you will plug in two vectors into the dot product, and on the other end you are going to get a value which is a scalar value, so you're not getting a vector back. So we will start with the dot product. The book talks about two different forms of the dot product. One that utilizes components and the other one that utilizes magnitude and the angle between them. I will start with the dot product that is represented by multiplication and addition of the components. So the theorem for the dot product is that if you have two vectors, vector u with u1, u2, and the vector v, which is v1 and v2 components, the dot product of u dot v is equal to u1 times v1 plus u2 times v2. And that is equal a number. So that would be the formula. Very straightforward to compute. Let's say you have a vector 3, 7 dotted with the negative 1, 4. You will say 3 times negative 1 plus 7 times 4, that's negative 3 plus 28 equals to 25. What is the dot product? Yes?
Why are you saying dotted instead of times?
Well, the dot product is this higher creature in the world. So multiplication, the times, is, should I say reserved for 1D? I don't know. I already said that the dot product, well, I didn't say it yet, now I'm saying it. Dot product can be done on any dimension. So you have the 2-dimension version here with a 2D vector that only has x and a y. For a 3D version, which I'm going to write next, it will have u1, u2, u3 times v1, v2, v3. That will be a 3D vector times the 3D vector. You are still going to get a scalar component at the end. So one-dimensional dot product is your good old multiplication tables from your grade 2 or whatever the hell you wanted. I learned in second grade. So multiplication table from that time, that is your one-dimensional dot product, and you say times, right? Then you have 2D dot product, which is you multiply two vectors with the quantity, and then we keep going. For the 3D now, it's going to be the same. So this is a 2D version. Let's take a look at the 3D version. So we have that the vector u is u1, u2, u3, and vector v, which is v1, v2, v3. And what we do with this is the dot product between vectors u and v, so u dot v is going to be, oops, not a vector, sorry, u1 v1 plus u2 v2 plus u3 v3. And that would be the 3D version of the dot product. It works in any dimension, except in this class we are only dealing with two-dimensional and three-dimensional vectors. You take linear algebra, you will be dealing with nth-dimensional space, so you will be doing this in n dimensions. And obviously, where would we be without the annoying example for you to try? I'm not going to write this, so let's just dot two vectors. So 3, -2, and 4 dotted with 1, 2, 3, very creative vector. Can't even think. It's original. So 3 minus 4 is -1, plus 12 is 11, right? So 3 times 1 plus -2, no coughing, times 2 plus 4 times 3 is 11, clearly. Good. So that will be the dot product. Now we're going to take a look at the other form for the dot product. The other way to define the dot product would be to write it as the product of magnitudes of two vectors multiplied by the cosine of the angle between those two vectors. Also works in any dimension. So for this one, it's labeled as the definition. The dot product in any dimension, uv, is going to be magnitude of u times magnitude of v times the cosine of theta. And the cosine theta is the angle, right? Theta is the angle between vectors u and v. So we are talking about this situation. You have a vector u, you have the vector v, and this angle in between is the angle theta. Now this is a very powerful tool because it gives us that theta is equal to the cosine inverse, right, of u dot v divided by magnitudes, the product of magnitudes. This is the formula that you will use to find the angle between two vectors. Is that important? The answer is hell yes, it is important, right? If you have two ships tugging a bigger ship, right? What are the angles at which they're connected with those chains or cables or whatever? You hang the painting that has the rope or the whatever, the tension, all of those angles there, because forces in cables are vectors. And if you have two of those, then you have the angle in between them. So that's the dot product already. It's involved in many things. When you are pushing the object, remember what I said, parallel, your hands parallel to the arms, parallel to the surface. So all of that plays the role, and this is the formula that we use to calculate the angle. Maybe I put this one in the distinguished box, right? Because you will be using this one. What do we say about coffee? So find the angle between vector u 109 and vector v -3, 3, and I'll run out of numbers. 5 it is, thank you. You know how to find magnitudes. You know how to find the dot product by multiplying components. And your calculator should have that cosine inverse button. Now, if you are using your cell phones, I think if you flip the calculator sideways, you should be able to get the inverses. And if you... What?
This is the last time I'll be there, I'm sorry.
If you guys have proper phones, then you can download the app which has the EI384 and whatever else. If you have Apple phone, you just go in the garbage, take the real phone, and then install the app, and then you have it. What can I tell you? It is what it is. So there is this app that is for Droid-based phones that you can download and then install free. And then you can have any of the TI family calculator on it.
Just called TI calculator.
No, it's called the Bitamu or something like that. No one can spell this thing. I think they went for Wabbit because it does have a rabbit in front of the calculator. It's invisible ink, so just figure it out. W-A-B-B-I-T, and then other letters as well. As soon as you type all of that, type in first 4 letters, you get it. Wabbit. Wabbit. Oh, it's a Wabbit emulator. EMU. Oh, I just figured it out. Been using this for almost 2 years now. Yeah, the Wabbit emulator. All right, there you go.
Oh my god. It's not gonna make calculator.
Yeah, so any of the 80 series or 90 series is there as a ROM.
Anyway. Oh my god.
Yeah, it's fun, right?
Yeah, that's hilarious.
What's the angle in degrees? You can just have 1 decimal, let's say. Make sure your calculator is set to degrees because it's most likely in radians if you graph stuff. So, exactly 45 units? That's 45 units. Wow. Who contributed 5? You contributed 5. That sealed the deal, man. Wow. You made that possible for all of us. Thank you. Anytime? Wow. We'll check next time as well. We'll come to you for the number master. What was the class I was working out? I think it was it Saturday or or a Calc 2, I don't know, in one of classes, I asked students, give me the number between 1 and 16. And the student says pi. And I'm trying to do a homework exercise for everyone to understand. Needless to say, he was disqualified.
Okay, so I'm a bit rusty, but inverse cosine is, it's not identical to any other trig function, is it? It's like its own thing?
Yep.
Inverse cosine?
Yep.
Okay.
So we have theta is equal to inverse cosine of the dot product, which is 109 dotted with negative 3, 3, 5, divided by the multiplication of magnitudes, which is 1 squared plus 0 squared plus 9 squared, and then you have negative 3 squared plus 3 squared plus 5 squared. The cosine inverse stays for now. We have to compute, so negative 3 and 0, and then 9 times 5, 45, so 42, I hope. And then in denominator you have square root of 82 times, the other one is 9, and 9 is 18, and 25 is a lot, right? I'm sorry? Yes. Very good. And all of this is about 45 degrees, and done deal. So 45 degrees. Make sure that you are, be very careful with your calculators, that mode button, right? You need radians. You need radians for graphing, and most of the angles that we get in class will be the degrees, because we love your engineering. Good. Awesome. So now, thinking about this formula, you have that u dot v is equal to magnitude of u times the magnitude of v times the cosine theta. First thing we see there is that clearly if the vectors u and v exist, their magnitudes are not zeros, right? Otherwise there will be zero vectors there. So if these are non-zero vectors, they will have these values. But cosine theta could be zero, right? So this is not zero. Magnitude of u times magnitude of v is non-zero, say. But cosine theta could be zero. In which case we get that u dot v is 0. For which angles would that happen?
If they're perpendicular?
Very good. So for cosine of 90 degrees or 270 degrees, by pi over 2, negative pi over 2, and so on, when vectors u and v are perpendicular, the dot product is 0. And when dot product is 0, that means, right? So this is one of those theorems that goes both ways, right? We call that if and only if. So if the dot product is 0, vectors are perpendicular, or if the vectors are perpendicular, the dot product will be 0. So we can write that as a theorem and say vectors u and v are perpendicular if and only if u dot v is equal to 0. The statement if and only if, especially for the honors, means the theorem works both ways. We don't have every theorem work both ways, right? Some theorems work only forwards. And then you have that if-then, right? If this happens, then that happens. That would be a theorem. Now, when you have if, so the problem can have this. You would know that vectors are perpendicular, or the problem could say perpendicular vectors, blah, blah, blah. You immediately know the dot product is 0. Yes?
What's the notation for if and only if?
EFF. IFF, sorry, IFF.
That's like the proof notation?
Yeah, for proofs, if and only if is just if. That's what it is. All right. So we have that, and obviously holds for any dimension, except later on, after 2 dimensions, we say orthogonal for 2 things. So you would say that 3 vectors that meet in a corner, right? You have x, y, so I, j, k unit vectors. They're orthogonal to each other. We don't say perpendicular. Perpendicular is kind of 2D word, reserved for 2D space. So, good.
So orthogonal is just 90 degrees?
Yes, that's the word for n-dimensional space. Orthogonal means 90 degrees. So orthogonal or perpendicular. Properties of dot product. Commutative property, u dot v is the same as v dot u. So all of these properties, again for honors section, the proofs, where you calculate one side, calculate another side, and you see that by the basic commutative rule from your regular multiplication, you can show their equivalent. U dot v, the associative property, so you can go cu and then dot v, or you can go u dot cv. And distributive property for the dot product. No coughing.
Oh, that one?
So those would be the properties. That's the W. In all its glory. All right, so what happened? Over here, there are dots, the dot product. Find the angle between U and V. So here's U, 2y minus 3k. It's a unit vector, so I'm going to put hats. And here's V. I plus 4j plus 2k. So find the angle. Yes, it is a hat. Do you need to zoom in? Hat. So again, theta is equal to cosine inverse, and then we have the dot product. So 2, 0, negative 3, dotted with 1, 4, 2. We agreeing on that? IJK. So there's no j in vector u, therefore it's 0 for the middle component, the y spot. And then we have the square root of 2 squared plus 0 squared plus negative 3 squared, which is same as 3 squared, square root of 1 squared plus 4 squared plus 2 squared. Everything equal to cosine inverse of 2 minus 6 is negative 4, I hope. That looks like a 6. And then we have 4 and 9 is the square root of 13 times 1621. Good? And what's the angle approximately? 1/4? Like this? All right. So 2 more things regarding the dot product. Well, actually, no, 3 more things, because we also have the application. Um, so we have this part where we talk about projections. So orthogonal projections orthogonal projections. And the textbook has an awesome visual on it. So imagine that you want to project vector u onto v. So v is the base. So technically you are looking for the shadow as you shine the light perpendicular to the v-axis because you are projecting onto v. All right? So listen to the language. Projecting onto v, you project the light and whatever shadow falls would be the projection. So the vector u is going to be scaled, so just this shadow, and it's going to be in the direction of vector v. This is actually very important in physics and engineering. So now you have the projection. If the vector goes the other way, right, the projection is on the other side, it's just a negative, right? So you have all of these possibilities. Yes?
So there's no z-axis in those pictures?
No. Projection, this is a 2D projection. So let's have,
What on earth?
there we go. And then as you drop, there is the projection vector right there. So this vector over here, yes. I know, it's tough. So I have vectors u and v, and I project orthogonal projection, which is 90 degrees. We have a projection of vector u onto v. So onto is a small, right? That's like a base. That's going to be a small value there. And then u is the larger one. So what is the projection equal to? What do we get? We actually get u dot v over v dot v, everything times v. The bottom is the v squared. It's v dot v. So you have to multiply the components. Yes?
Does dot product work like the way multiplication does, where you can cancel that v out on the top, on the side with one of the ones on the bottom?
Nope. Yes.
Is a subscript v, like projection subscript v, does that mean you project it onto?
Yes. So I'm going to actually spell that out.
I can't see the denominator.
V dot v. So this one over here says projection of u onto v. So v is the base. Now to address further your talk about the magnitude, we are actually getting a vector, because if you carefully look at this, u dot v is going to be a scalar number, 7. V dot v, again the dot product, let that be 3. So you have 7/3 here. And you have vector v, which is vector. So now you have a number times the vector, so it's just scaling the vector, shortening or making it longer. What is the direction of this projection? What's the direction?
Same direction of v.
Same direction as v, right? Because the projection of u is happening onto v, right? V is that base. So if you are on the inclined plane, right? If you're an inclined plane and you have a force going this way and then a force going that way. So technically, think of it as, actually, let me do that on a tablet. So I'll explain it better then you will all understand a little bit of physics as well. These all have arrows because these are all vectors, obviously. All of them have arrows. These are all vectors. All right, so I will start explaining this projection through pushing the crate. On the surface. And what I have here is the force. Let's say you are leaning at the corner and you are pushing it like this. So what we are talking about is this situation, right? At the angle, I'm leaning and I'm pushing this. Now remember what I said before, that you don't get to bury this object into the ground, right? Because you can't. Now, which way the force actually goes? The force actually goes this way. So if you think about this as vector v, and this is vector u that you are actually pushing with, it's this portion here, which is the projection of u onto v, because all of the force has to be forward. As I push this desk, I can't bury it into the ground. So all of the force is forward. And all of the force is coming from me pushing as a vector u. So now the projection onto v, this is the only component that does work. The rest is wasted. Yes?
So 2 questions. One, it's not just the horizontal component of u.
It is.
It is? So would you just use cosine then?
Yeah, you would.
But like, we wouldn't have to do the projection then.
Yeah, but if you put all of this on incline, then you have to mess more.
You're right. So then, and then the second thing is, what is the answer? What form is the answer in?
It's going to be a vector. You get the vector back. So we'll do the example. One more hand. Who else had the hand?
Oh, no, that was my question. I was just gonna say, I kind of figured like this is easier in 3 dimensions than trig, which is 3 dimensions. Right?
Yeah, this for 2D.
It's kind of.
It's easy. Yeah. So now, let's calculate some of these projections and see. So I'm just going to say project vector 3, 7 onto -1, 2, whatever. All right, let's see. So this is just a straight up plug everything in a formula, grind it through, get the number at the other end.
Once you take that from the formula, once you take the magnitude, you can do the dot product, all that onto it.
When you find all of the magnitudes and compute the whole thing, it's just a number. You multiply that into the vector, right? Because that whole thing is a scaling factor. Yep. It's a scalar, so it just scales the size of vector v.
Why is it in the bracket?
Is it the length of, yeah.
Yeah, it's a positive number. Distances are always positive. You have two dot products, right? Dot product divided by dot product. So that has to be a number divided by number, right? So it will always be a fraction 3/4 or 1 or 7, right? It's going to be some number there.
People had parentheses there.
Same. Right, so let's take a look. The projection of vector 3, 7 onto vector negative 1, 2 is equal to, well, you want parentheses here.
No.
It's important to make you happy. No, this is calculus class. It's important for everyone to be happy at all times, like in any other math class, except Calc 2. Sequence and series, just blood, sweat, and tears, right? I know. I'm sorry to disappoint. There will be no sequences and series in this class. But differential equations will make it up. Okay, the entire chapter. So 3, 7 dotted with negative 1, 2 divided by, no coughing. No, the only reason why I say is I know because you have to cough. That's why. Had earlier discussion with someone about me always saying the worst possible thing, whether I mean it or not. It doesn't matter. It's just the urge to say it. After some time, you just start filtering 60% of what I say. Remember directional cosines and, you know, those kind of things that they'll be useful. Partial derivatives. The coughing thing, no one cares. We have 14 minus 3, 11, divided by, that's 1 plus 4 is 5. I don't need parentheses, it's just 11/5. Times negative 1, 2. So it's negative 11/5, comma, 22 over 5. And that's the vector.
What does that look like? Like if you figure it out.
It's going to look like technically anything else. You have any other problem we did. So it's going to, let's draw exactly how it looks like, because we can. I have 3, 7. So this is vector u. And then we have negative 1, 2. It's vector v. So clearly, or should I use that word, I'm supposed to extend this. So I'm going to use maybe blue. Extend this one forever. And then draw the perpendicular line. So there's 90 degrees over here. So this vector here is the projection vector. Now, as always is in mathematics, things just fascinating in terms of how everything works every time. You see that this short vector here is actually shorter than the projection vector. And you see that in your calculation where the vector v, which is the black one over here, was multiplied by a number that is bigger than 1. This is even bigger than 2, right? Technically, more than double, right? So, see that? And that's more than double right there. So, in this case, it's stretched vector v to accommodate, so it's a projection. Where is the light? The light is right here, right? right? The light is right here shining this way, and this vector casts the shadow. So this red thing over here is the shadow. So yes, for that very basic physics problem with the crate, sure, cosine solves it. You're done, right? One step. But what happens when that is on the incline, right? And you're on the incline and you're pushing not perpendicular to the incline, oh sorry, parallel to the incline. If you push perpendicular to the incline, you're not getting anywhere. The normal, that's the job for normal force. Yes.
Where is that light from? Like, is it coming from, like, relative to the vectors? Where is it coming from?
What do you mean?
That light that you're referring
The light, I gave you the
So it's just
motion,
coming
right?
from-
The light is coming in this way, and as it shines, right? This is a shadow, so light has to be here. The light source is this side. In this case, the example in the book was on top because light is always perpendicular to the surface, right? The last ray, right, that doesn't make it is the very tip of this. And then the next ray is the one that illuminates the next location.
So it's perpendicular to that vector.
The light is always perpendicular to V, the vector that you are projecting onto. Light is always going to be perpendicular to that, which is the reason why I have a 90-degree angle here, because the shadow starts there. Quickly before he comes back, the calculus 3, closer to, calculus 3 is all about, well, not all about, but mostly about memorizing a lot of these formulas and things, procedures. We really don't give formula sheet for calculus 3 because that is actually all you are learning. Memorizing this formula for projection is what you are learning. Later on, different integration and stuff, because if you have the formulas, this course is technically Calc 1 and a trig course. That's the prerequisites. So with the formula sheet on the exam or any of the exams, you guys would technically be doing pre-calc and Calc 1 all the time. Do you know how to differentiate? Do you know how to integrate, right? So memorizing formulas for dot product, memorizing formula for projection, later on memorizing formula for curvature, memorizing formula for length of the 3D line, and so on. Those are the formulas that you are learning in Calc 3. Those are the Calc 3 concepts, and that's what you are supposed to learn in this class. Mechanics of doing problems. What have we done? Inverse cosine, you know that from before. Eventually we're going to differentiate, integrate, do the chain rule. That's all the stuff you know from Calc 1. So in first chapter, there's I think the most memorization happens in the first chapter, then it kind of dies off a little bit. But the whole Calc 3 is just technically that, and trying to kind of visualize these things so later on you can put the shapes together. The last thing I want to talk about here is work. See how I perfectly timed that?
He was telling us how hard this course is.
So as we are talking about the application, we are going to say, and we are talking about the crate that was moving, the work that we put, we know is force times the distance. But that's only when everything is parallel and nice. As soon as you start, right, if you're not pushing the crate right way, you introduce angles and so on, some of your work is wasted. So the formula that we want to know is that the work is equal to the good old vector dotted right? With distance, which means you go forward, which is in term our good old F times D times cosine of theta between them. And now you can go on the incline, you can go anywhere you want. So this is where the physics gets interesting. Like, not when you're pushing something along the floor left and right, but something when you're pushing at the angle on the incline and so on and getting these things. So again, you will get the vector force, right? F is going to be, I don't know, 375, and then the distance, 3 meters in one of the directions or all the directions. You just dot those two and you're done. Maybe we can.
Never actually looked at it like that. It's because in physics, force and distance are so equivalent that they actually still go together nicely.
Yeah. Welcome to my class, Solve Physics here. You can boo all you want. This is going live. All I need to say is your name, and you're doomed. When I mention your professor should watch my 11.3 stream. So now I got leverage. Yeah, he booed physics publicly. Problem 40 says a constant force F of 432 in newtons moves an object from the origin to 860 to point 860 in meters. So what's the work involved in this? You can make them. I told you that to which point it's going, from which point to which point. What can you get when you have 2 points? You can get the vector, right? So last time, remember the PQ, QP thingy? So when you have 2 points, you can go terminal point, which is 860, minus origin. So the actual distance vector here is 860, right? Because you are subtracting zeros. 8 minus 0, 6 minus 0, 0 minus 0. So the distance, and that's going to be in meters as units. And you also have the force, 432, in newtons. And what do we do for work? Dot product between the two, 860, dotted with 432. And what do we get? Hello? Exactly. So 50 Newton meters when you do the dot product. So 8 times 4, 32, 6 times 3, 18, 0 times whatever the number is 0. So when you add them, you get 50. With what force was this pushed? Yeah. Can we know that at all? Yes, it's magnitude of the force, magnitude of F. So 4 squared, right? 16, 25, 29, root 29 newtons. That's what, 5.47? So that's the force. So you can know you know also with what when the vector is given, it's a very powerful thing because it gives you with how much force you push and also in which direction, right? At 4, 3, 2. And then you also have the distance that it covers. Can you tell me how far it went? Yeah, it's the magnitude of 860. So it is not just that you calculate work, but given this information, you can also extrapolate how much force, how far it went, right? There are all of these others. So physics is extremely cool.
It's like the whole world around you, every last thing you see, feels that much more complete.
Yes, when you know physics.
And chemistry is just big physics. Biology is just big chemistry. It's all physics, man.
Yep. Well, you know where I sit, right?
No.
Look
You
at
know
that.
physics. What?
It starts right there. And then physics eventually catches up, and then engineering after another 300 years, and then yeah. And then we have iPhone. So we can differentiate how the cool things look like. Right, good. We're done with 11.3. I'm gonna stop the stream. I'm going to say more awful things about Apple during the break, and then we'll resume with 11.4.